Hello, everyone. Welcome to FIT's online tutorial day 2. Good morning, good afternoon, or good evening. One apology at the beginning. As I wrote you all, I mistakenly wrote the starting time of the tutorial to be 13:30 UTC in one of the emails which I sent you in advance. The correct starting time is 11 UTC, and the tutorial begins at 11 UTC every day. Sorry for that. And as usual, let's start with administrative announcements. As I asked you yesterday, when you have questions, if your question is general or quick questions, please send a chat message to all tutors or other participants. I will answer them. If you have your own trouble or your specific question, please raise hand. Tutors take you to a breakout session. Recording and guidance of this tutorial are available from the URL here. From here, you can download the video, chat recording, and also the guidance of this tutorial, in which you can find the rules or guidance on how to take this tutorial. And today, we are going to take a group photo. Please make your webcam and yourself ready. Lastly, please install Python and its libraries if you would like to take the optional course, Medical Data Treatment by RT-FITS on Friday. And the guidance on how to install Python and its libraries are available from URL here. I should mention that this is not 90% unnecessary for Windows users. This installation of Python and Python libraries matter to Linux and Mac users. If you have any problems or questions on Python installation, please ask questions to tutors. If everything is all set, let's go on to the first session of today. The first session of today is setting of various sources, tutorial course named Source A. In FITS folder, please go to Lecture Advanced Source A. Please go to FITS Lecture Advanced Source A. As yesterday was dedicated to review exercises, but from today, we'll be going to advanced contents. And Source A is the first advanced contents that we are going to learn in this advanced tutorial. Again, FITS Lecture Advanced Source A is the folder. And here, please open the PowerPoint slideshow and sourcea.inp input file. All right, let's get going. So, as the name of this material says, we are going to study the way to define sources. Indeed, we learned to define sources in basic lecture 1, in basic lectures, in which we defined the way to define neutron sources, so photon sources, of monochromatic sources. The point here is we are going to learn, for example, sources with the energy distribution. as long as alpha particles or gamma rays were the source, monochromatic sources were good enough. But for example, if you'd like to use beta rays physically have finite energy spread, and we are going to study how we can define energy distribution of the sources in FITs. Another thing we are going to learn is to define RIs as sources like cobalt-60, and we are also going to learn how to define more than one source, for example, 2 sources in one simulation. They are the goals of this lecture. Source A.inp is at first an input file in which projectile is 150 MeV protons, a pencil beam with a radius of 1 centimeter. A geometry is water cylinder with a 10 centimeter radius and a 10 centimeter thickness, 20 centimeter thickness. And 2 tallies are a T-track for fluence distribution visualization, and T-cross for proton energy spectrum tallying. 2 tally protons coming into water. This is the table of the contents of source A. First, we are going to learn the way to define sources with energy distribution, continuous energy distribution, and discrete energy distributions. Then we go on to set up of multiple sources, RI sources, and then summary for closing. Source with energy distribution. A source energy can be defined either as monoenergetic or distributed in FITs. And monochromatic sources are what we learned in basic lecture. And in this tutorial, what we are going to work with is these sources with energy distribution like this one. In this case, for example, the proton beam is not monochromatic, but it has energy distribution from 0 to 150 MeV. This is a short instruction on how to set the energy spectrum. By default, in this input file, source A, there is a E0 parameter, which is 100 to 50. And this parameter is the one which defines the energy, 100 to 50 MeV monochromatic. By commenting out this line and define E type equals 1, followed by NE equals 2, and then 0, 50, 100, and 41, this set of parameters are responsible for energy distribution. In this way, we can define energy distribution from 0 to 100 MeV. As a general rule of FITs, the unit of energy is MeV or very occasionally angstrom. Usually, the unit of energy is MeV. There are some more ways or some more explanations on how to define energy distribution of the sources. There are actually 3 major ways to specify energy distributions. E-type 1 is the one that we used in the previous slide, E-type 1. By using E-type equals 1, we can define continuous distribution with integral values. If you define E-type to be 21, a continuous distribution with a differential value is going to be the definition, which I'm going to explain you later. And E-type equals 8 is also useful because by that you can define discrete distribution. like one energy peak at 1 MeV and another peak at 2 MeV. To define continuous distributions by using E-type 1 or 21, though the syntax is like this: E-type equals 1 is the first line of energy distribution, and this line is followed by NE equals, this is fixed format, and this N means the number of energy bins, which is either 1, 2, 10, or 100, whatever number, integer. And then following lines, this line is followed by n plus 1 lines, which define energy points E1, E2, E3, which are, for example, 1 MeV, 2 MeV, 4 MeV, etc., etc. And these energy points are followed by the amplitude of the source at this energy bin. As we define the energy bin initial point and second point and the intensity between first and second point, we will have n plus 1 energy points and n amplitudes. When it comes to discrete distribution defined by E-type equals 8, E-type equals 8, this fixed format is followed by NE equals number again, but this time this NE equals number is followed by N lines corresponding to the energy and the amplitude at that energy. Let's go on to an exercise. Exercise number 1 is an exercise to set proton beam with an energy distribution from 1 to 50, 50 to 100, 100 to 150 in MeV, and the relative intensities in these 3 energy bins are 1 to 3 to 2, like the one on the right of this slide. The important tips to do this exercise number 1 is add E-type subsection and set energy distribution, as I explained here. Oh, and also please comment out the line E0 equals 150, because this definition and energy distribution competes. So please try exercise number 1. If you have a general question, please write in the Zoom chat. And if you are stuck for your own problem, please raise your hand to ask for a breakout session. So please try this exercise. Excuse me, I forgot to mention, when you finish this exercise, please turn on yes sign. When most of you activate the yes sign, we will be going on to following exercises. So please don't forget to turn on yes sign. And when you finish, please you can go to exercise number 2, 3, so forth. Thank you. How is the progress? If any troubles, you can ask the tutors, or I will be showing you in the screen. So now it's the time for answer of exercise number 1. The input file is initially like this. And we go to the source section, starting from line number 12. And there, first, comment out line number 16, because this is E0 parameter, which defines monochromatic source. Then, let's say at line number 21, E-pipe. One. And then we define energies, 0, 50, 100. And 150. Then we give the intensities in energy bins. The first energy bin, the intensity is 1. In the second energy bin, 3. In the third bin, 2. Let's run this input file. Terrible mistake. We need NE equals 3 because we have 3 energy bins. In this way, we can define energy distribution of the source, which can be confirmed by cross eng.eps. This is the T cross tally, which scores proton energy on the at the upstream of the water cylinder. In fact, the intensities are 1, 2, 3, 2, 2 in the energy bins from 0 to 50, 50 to 100, 100 to 150. So this is the answer of exercise number 1. Then let's go on. Exercise number 2 is an exercise to change the energy bin from 100 to 150 to 100 to 200. As we defined 3 energy bins with a of 50 MeV, we are going to change the energy bin of the third energy bin, whose in particular, the upper limit of the energy is changed from 150 to 200. That is this exercise. So please try exercise number 2. I think this exercise is not very much complicated because now it's time for the answer. Exercise number 2 is an exercise to change the upper energy upper limit of the third energy bin from 150 to 200. This, at line number 26 in my input, this is the parameter to be changed. In fact, by running this input file, EPS file is updated to be like that. Again, the energy bins are from 0 to 50, from 50 to 100, from 100 to 200. The intensities are 1, 3, and 2 in speaking in terms of the area of the intensity. This is going to be important in exercise number 3. Exercise number 3 is an exercise to change the E-type parameter to define the intensity ratios as differential values. So exercise number 3, please simply change E-type from 1 to 21. What's important in this exercise is to understand why E-type 1 and 21 is different. So please try this exercise. All right, now it's time to show the answer. Exercise number 3, what we do is very simple. At line number 21, where I define E-type parameter, please change E-type parameter from 1 to 21. That's the only thing we do in this exercise in the input file. What is important here is to look into the output file, this EPS file. We see that the energy bins haven't been changed from 0 to 50, 50 to 100, 100 to 200. We have 3 energy bins. But this time, the height, the amplitude of the source in the third energy bin has been doubled. It's twice as high. This is actually the meaning of E-type 21. Previously, E-type parameter was 1. E-type 1 means to give the intensity as integral values. So this was 1, 2, 3, 2, 2 in integral. But the answer of exercise 3, the intensities are given in differential values. So the differential, which is the integral divided by the widths, is 1, 2, 3, 2, 2. The area divided by the widths, whose width is double here, which is eventually twice as high compared to integral definition. In other words, by using E-type equals 21, we can define energy spectrum as differential spectrum. This is what we learn in this exercise. Please choose E-type parameter depending on the unit or normalization of your source energy distribution. That's the lesson. Let's go on to the next part, discrete energy distribution. There are sources with energy distribution. For example, cobalt-60, cesium-134, they have multiple gamma peaks. For example, cobalt-60 has 2 energy peaks at 1.173 MeV and 1.333 MeV, 2 gamma peaks. And these are gamma rays emitted after beta decay to this excited state. In exercise number 4, let's define our source equivalent to cobalt-60. First, please change the source particle species from a proton to photon. Define an isotropic point source. To be precisely speaking, change the source radius and direction to be something. Use E-type equals 8 and set the photon energies of 1.173 MeV and 1.333 MeV with intensity ratios of 1:1. And finally, please set T cross to tally photons, photon fluence from 0 to 2 MeV because the maximum energy is 1.333 MeV. We no longer use 100 MeV protons, so please don't forget to change the energy binning of T cross tally. So please, by following these instructions, please try exercise number 4. Enjoy. All right, let's go on to the time for answers. Basically, what we do here is to follow the instructions here, change the projectile from proton to photon, change R0 parameter to be 0, because we want a point source, and change DIR from 1 to ALL. As we learned in one of the basic lectures, this ALL means to emit particles isotropically. E-type is 8 because we want discrete energy distribution. ME, number of energy points, is 2 this time. The energies are 1.173 and 1.333. The relative intensities are 1 to 1. As these numbers intensities are relative, you can do in a way like 0.5, 0.5, or if you want, 100 to 100. Everything is the same. Then let's scroll down to T cross tally from line number 86. And there we change the energy binning. The minimum is 0 MeV. The maximum is 2 MeV. And number of energy bins is 200. Then we run this input file. Oh, and my mistake, photon. By doing all these, we can change the source to be a photon source with the energy distribution like cobalt-60. Actually, in cross-ENG.EPS, we see 2 peaks. The height are slightly different because of the randomness of the random numbers. But anyways, the relative intensities are 1 to 1, and the energies are 1.173 and 1.333. This is nothing but cobalt-60 source. Then let's go on to the next subject, setup of multiple sources. In fact, we can define more than one source in one simulation. Multiple sources with different radiation types, positions, or energy distribution can be defined. Actually, one of the questions in Zoom chat was whether we can superimpose our E-type 8 source and E-type 1 source. The answer is yes. By defining 2 sources at the same position, we can superimpose 2 sources. For example, our cobalt-60 source is actually a gamma emitter and beta emitter at the same time. So you can, for example, define beta source and gamma source as 2 different sources using a this multiple source function and locate these 2 sources at the same position. Then you can effectively make cobalt-60 source emitting both beta and gamma. You can make use of multiple source function in this way as well. Suppose there's a target and this target is exposed to 2 different sources with different intensities. By defining 2 sources using a multi-source function, you can make a simulation configuration like this one. This is a way to set how to way to set multiple sources. In source section, to set multi-source subsection, we define multi-source subsections starting with a triangular bracket source and closing bracket equals relative intensity, which is a number. And we set total fact to normalize the total source intensity. For example, a total fact is 1, and this total fact 1 is followed by triangular bracket source equals 2. And this means that this source, the first source, has a relative intensity of 2. And the next multiple source subsection start with triangular bracket with the source equals 1. This means that the second source has an intensity of 1.0. And the third source, it has the intensity of 3, and the details are defined here, as well as the other sources. And here's an indication on the normalization, a negative or positive of normalization factor. If normalization factor is positive, like this, positive 1, the particles are sampled randomly from 3 sources following, and the sampling probability of 3 sources follow the relative intensities. If this total fact is negative, for example, minus 1.0, 3 sources are equally sampled, but the intensity is corrected by the particle weight. So minus 1, a total fact equals minus 1 is useful if some of the sources of multi-source have very low intensities, but you would like to consider such low intensity sources. In that case, you should use minus total fact. Let's go on to exercise number 5. Set cobalt-60 sources at the left and right of the cylindrical water from Z-10 to 40 with intensity ratios of 2 to 1. One of the sources has intensity of 2, and the other has the intensity of 1. To make multiple sources, please add triangular bracket source lines to define 2 sources, and put 2 point sources at position Z equals -10 and Z equals 40. To do that, please change Z0 and Z1. Lastly, define the relative intensity of the left source and right source to be 2 to 1 to realize this ratio. Please try exercise number 4. When you finish, please turn on yes sign. And if you have problems, questions, please write on Zoom chat or raise hand to ask for a breakout session. So please try. How is the progress? If you are stuck or in trouble, just in case, I will be showing you on the screen. So, exercise number 1, the goal of this exercise is to define multisource. We keep tot fact, but we add triangular bracket having source inside and equals 2. This source, a multi-source definition means the intensity is 2. The details of the first source is fine. Projectile is photon. Its point source at z equals -10. Direction is isotropic. And it has 2 energy peaks. Then we copy and paste the section to make the other source. The intensity is 1, which can be defined by this triangular bracket source. S type 1 photon, but the position is -40. So Z0 and Z1 are -40. Everything else is fine. Let's run. This time, we look at track xz.eps. Oh, no, there is something wrong. Sorry, this is not -40, but +40. Thank you, everyone, in the chat message. Yes, now we have 2 sources at -10 and +40. Let's go on to the next subject, Ri source. This function, Ri source, is very powerful when you would like to use radioisotopes. By using this function, alpha, beta, and gamma radioisotope sources can be defined by simply specifying the name of Ri and its activity from version 2.86. What we were doing in previous exercises were to define the energies of a cobalt-60, for example. This works fine as long as you know the energies of gamma peaks. But I'm pretty sure that none of us can remember the energy spectrum of beta rays from cobalt-60, for example, because it's complicated distribution. And I can hardly remember from which energy, maybe 0, to up to what energy the beta rays of cobalt-60 range to. And this Ri source function is a way to define Ri radioisotope sources in automatic way, just by defining the name of Ris, like CO-60. To use Ri source function, the rule is simple. By defining E-type equals 28 or 29, we can quickly use Ri sources. 29 is the mode to change the weight of the sources. So usually we use E-type 28. E-type equals 28 format is like that. E-type equals 28. This line is followed by Ni, please be careful, not E, but Ni equals number, a number of Ris. And this line is followed by N lines. The first line is composed of the name of Ri and its activity in back row. The second line is another Ri and its activity. In this way, you define n Ris, and these lines are finally followed by normalization parameter. It's either 0 or 1. 0 is the default. Everything is normalized per second. If you prefer normalization by a source particle, then you can choose 1. Let's go on to exercise number 6 to define cobalt-60 sources of 200 and 100 becquerels in the left and right of the melt sources that you defined just before. To accomplish exercise number 6, these are the guidance. Change E-type from 8 to 28. Specify cobalt-60 of 200 and 100 becquerels at Z minus 10, Z equals minus 10, and plus 40, respectively. You can use either CO-60 or 60CO. And normalize the tally result to the unit of per second, which can be defined by norm equals 0, which is default. And please be careful that our taught fact should be the number of melt sources when you use Ri source. So in this case, we will be having 2 Ri sources, so taught fact should be 2 in this case. Please try this exercise number 6. Then let me explain this exercise, exercise number 6. Exercise number 6 is an exercise to replace your handmade cobalt 60 with cobalt 60 defined by RI source function. To do that, the most important thing is to change E-type parameter from 8 to 28, because E-type 28 is the key to use RI source function. And this time, this is not an E, but an I. And this NI is followed by cobalt specification of RI. This time, CO60, 200. This means cobalt 60 of 200 becquerels. This time, we want to use per second normalization, not per source normalization, so it's 0. But this is default, so you do not have to define this parameter explicitly. And in addition, it is important to change the source intensity of multi-source definition to be 1 because the intensity of this source is defined here. We don't need normalization by multi-source specification. Scrolling down to the second source, we again do the same. E-type equals 28, and I 1, and cobalt 60. This time it's 100 becquerels, norm 0. And finally, tot fact, when we use RI source function, tot fact should be the number of multi-sources. This time, there are 2 sources. By doing that, the outputs are pretty much the same because they are both cobalt 60 sources. As we have spent 1 hour, let's have 10 minutes break. After 10 minutes break, we will be resuming from this page. So please take a break. Thank you. Welcome back, everyone. Let's resume from the slide number 27, explanation of the decay time and daughter nuclide. In other words, this slide explains how Fitts RI source function considers the decay equilibrium. This is important because some isotopes needs consideration for decay equilibrium to simulate their gamma rays and beta rays. For example, cesium-137 is well known as the gamma emitter of 662 keV gamma rays. But precisely speaking, it's not cesium-137, but its daughter nuclide, barium-137 metastable, is responsible for emission of these gamma rays. Without consideration for decay equilibrium, we cannot simulate gamma rays from cesium-137, which is very common RI source. For that, we need D time parameter to consider decay equilibrium. A D time parameter is -10 by default because a D time -10 is usually justified. Let me explain D time, the meaning of D time, and how we can choose right D time. When D time is 0, this is very simple. This is D time equals 0 means that this is a freshly made RI source. In case of cesium-137, D time equals 0 means that this is composed of cesium-137, pure cesium-137, without barium-137, its daughter nuclide. This is the case when you use our RI source, freshly separated and made without contamination of other daughter nuclides. So in this case, this cesium-137 does not emit gamma rays. And D time equals 30 years is also simple. In this case, this cesium-137 100 becquerel is reduced down to 50 becquerels because 30 years converted to seconds. This 30 years is one half-life of cesium-137. And this 30 years is long enough to let barium-137 metastable reach its equilibrium. So the activity of barium-137 metastable is also 50 becquerels. So this description, cesium-137 100, D time 30 years, creates a source of cesium-137 with 50 becquerels and barium-137 metastable in its equilibrium. What's tricky is negative D time. When you give D time to be -1, Fitts calculates that this source, for example, cesium-137 source of 100 becquerel was one half-life ago. So one half-life ago means 30 years ago. So 30 years ago, cesium-137 must have been 200 becquerels. And when this source was made, barium-137 metastable must have been 0 becquerels, because this is the point when the source was freshly made. And 30 years, one half-life, is long enough for cesium-137 source to reach equilibrium with the barium-137. So the cesium-137 100 d time minus 1 means cesium-137 100 becquerels and barium-137 metastable 100 becquerels. In this way, d time minus 1 or minus 10 is useful to consider a decay equilibrium, which is very often the case. Oh, and apparently, d time minus 10, the default value, is very safe because usually Ri sources are made a long time ago in the factory and provided to your lab when the Ri source reaches the decay equilibrium. In short, usually you do not have to think about the definition of d time because d time is minus 10 by default, which is usually long enough. So let's take an exercise number 7, change 200 becquerel cobalt-60 source to 200 becquerel cesium-137 source, and consider the radioactive equilibrium. To do that, please change cobalt-60 to cesium-137 in the first multi-source, and add d time equals minus 10 to the subsection, which is default, but let's do it explicitly to understand it better. So please try exercise number 7 and see if you really see cesium-137 source, gamma rays. Please try. How is the progress? Now it's time for the answer of exercise number 7. This time we replace the source, one of the RI sources, the first one, cobalt-60 with cesium-137. If you are lost, please have a look at the screen. I will be showing you how to complete exercise number 7. And just in case, one more thing to change is the time parameter minus 10. With these new parameters, cesium-137 200 and d time equals minus 10, we see a cross eng.eps, which looks like this one. We see 2 gamma peaks of cobalt-60, but at the same time, we see a peak attributed to cesium-137 here. And we see some X-rays from cesium-137. Anyways, in this way, we can simulate RI sources with taking into account for the decay equilibrium. Let's go on to the final exercise of source A. Let's define cesium-137 beta ray source. To do that, please change PROJ in the source subsection for cesium-137 from a photon to all. PROJ equals ALL means all types of radiations emitted from RIs are automatically considered as the source in the fit simulation. What this means is that if you say PROJ equals all ALL in, for example, americium 248 241, it will be a composite of alpha and gamma. This time, cesium-137 is a beta emitter, so we can consider emission of beta rays and gamma rays at the same time. And please don't forget to set part equals photon space electron in T-track and T-cross to see the trajectories and energy spectra of electrons as well as photons. So please try exercise number 8. And when you finish, please turn on yes sign. All right, the answer of this exercise is very simple. In the first multi-source subsection, PROJ, it's changed from photon to ALL. We scroll down. To T crystally to score electrons and do the same for T track. Let's run. Then now we see photon peaks and electron bit rates. In T track, we see photons and electrons, which are emitted from cesium-137. So in this way, we can ask FITS to assimilate whole cesium-137 source as the emitter of beta rays and gamma rays. This is the answer of exercise number 8. Lastly, here's a tips about RI source function. I told you that FITS automatically considers the energy spectra of gamma, alpha, beta rays, etc. of RI sources. But you can, when you have doubt or curiosity, you have an access to the definition of RI source inside FITS, looking into the input .out file, fits.out, created in the same folder as source A, input file. By scrolling down this source fits.out file, there is a source subsection in the echo part. And here, inside this source section, you can find how FITS interpreted your input file. In this case, we define cesium-137 of 200 becquerels, and the cesium-137 has X-ray peaks, this many X-ray peaks, gamma rays, and again, this has barium-137 in equilibrium. So this barium-137 metastable also has X-rays and gamma ray peak. Apparently, barium-137 ground state also have energy distribution. No, not really, because barium-137 is stable. So eventually, you can have a look at the breakdown of your RI source definition. In this case, cesium-137 and cobalt-60, which you defined as the second source. So in this way, by looking into fits.out file, you can get an insight into the spectral information of RI sources automatically created by FITS. So by making use of the functions we learned in the source A, we can define source energy distribution, continuous or discrete. We can define multi-sources by using triangular bracket source subsections. And we can define alpha, beta, gamma decay sources by using Ri source function. So let's go on to next subject. Next course is options in the same advanced folder. Please go to FITS lecture advanced options. And please open PowerPoint slideshow and transform.inp. This is the first input file to work with. Other input files, we will be using them later. Please open transform.inp and the slideshow. Again, please go to FITS lecture advanced options folder, and please open the slideshow and transform.inp. If you are ready, let's get started. In this in this lecture, we are going to learn complementary functions, which are not crucially necessary for simulations, but knowing these functions makes big difference in realizing, making your simulation easy or implementing very special features. The first thing to learn is transform function. This lecture is like omnibus, composed of 4 independent parts, and we take transform function as the first subject. This can apply translation and or rotation to the spatial coordinates of source, surface, cell, and magnetic field, as well as tallies. For example, if you define certain object, let's say water cylinder, you can rotate and you can apply translation to the components of your geometry. And here's an instruction on how to use transform function. To use transform function, the very first thing to do is to define a transform section. Second thing to do is to use this transform by setting TRCL equals number in cell, source, magnetic field, section, or etc. So 2 steps are define and use. That's very simple, isn't it? And transform section is structured in this way. As is true for all the other sections, transform section begins with a square bracket having a transform inside. And this line is followed by a definition of the first transform. And first transform is defined by various numbers and some fixed identifiers. The first column starts either asterisk or nothing. If you put asterisk on the top, the unit of the angles is degrees. If you do not put asterisk on top, the unit of the angles is radian. Whichever you put asterisk or not, the next column is TR number. This n is an integer number, and this number works as an identifier of this transform. So it's either 1, 2, 10, 100, 1000, something. Anyway, integer number. And this TR number is followed by 12, 13 numbers, sorry, 13 numbers. The first three are translation components of X, Y, Z. And when M, the absolute value of M, the final value is 3, either +3 or -3, the first three, next three numbers are XYZ coordinates of the center of rotation. Then next one set, two numbers means around which axis the object is rotated by an angle θ1. You can define another set to define another rotation around another axis. And you can also you can define one more rotation around another axis. And you can, of course, define the angle of rotation, 30 degrees, 60, right, 60 degrees, 1 pi radian, etc. Let's take an example. And before example, let me explain. M parameter. M parameter controls the order of translation and rotation. If M is positive 3, rotation comes first, translation comes next. If M is -3, translation happens first, rotation happens afterwards. Let's take an example. Example 1 is asterisk TR1, 005, 010, 0, 2, 45, 0, 3, -60, 0, 3. In this case, the meaning is rotate at the center of 0, 10, 0 around y-axis because M is +3, so rotation happens first. And this rotation happens having the center at this coordinate corresponding to these values, and rotate around y-axis. This y is meant by number 2. This number 1 is x, 2 is y, 3 is z. This time it's 2, so the axis of rotation is y by 45 degrees, because the top of this line is asterisk, so the unit is degrees. So this means 45 degrees of rotation around y-axis, and rotate around z-axis, because this is 3, by -60 degrees. After these rotations, translation along z-axis by 5 centimeters happens. In the same way, here's another example. In this case, M is negative, and there's no asterisk on top, using the radians as the unit of the angle. So in this way, we can define translation and rotation to be applied to geometrical components, magnetic fields, sources, tallies, etc. And here's a graphic guidance on the rotational directions. But probably you can learn it by actually defining the rotations. And this is no longer necessary because we use m equals 3 or minus 3, which are even more useful. But you can define rotation and translation matrix by defining m equals 1 or minus 1. By defining m to be either 1 or minus 1, the interpretation of these values turn to be something like this. But again, rotation matrix is twice as complicated as m equals 3 or minus 3, so we don't use this one. Transform.inp is at first like this. There's one water cylinder in vacuum. Exercise number 1 is an exercise to rotate the cylinder around the y-axis by 30 degrees, like this arrow. To do that, what we do are simple. Define a transformation in transform section and use it in cell section by defining TRCL. Transform section is already made halfway, so the only thing you do is to say rotate around the y-axis by 30 degrees and use it in cell section. So please try exercise number 1. When you finish exercise number 1, please proceed to exercise number 2, 3, up to exercise number 4. And when you finish exercise number 1, please turn on yes sign. If you are in trouble or if you get stuck, please ask tutors or other participants for help. Please try. All right, let me explain the first exercise. Exercise number 1 is an exercise to define a transform and apply it to one of the cells. Transform section has one transform, and this asterisk means the unit of angle is degrees. And TR1, this 1 means the ID number of this transform is 1. The first 3 digits are for translation, which is not important right now. And rotation happens with the center 0, 0, 0, so they are fine. We need to change this 0 first, as we are going to rotate this object around y-axis, so this is 2. As I said, x is 1, y is 2, z is 3. And the angle of rotation is 30 degrees. So these two values should be 2 and 30. Lastly, we put the RCL parameter at the end of cell a definition of cell 101. The RCL equals 1 because we want to apply this transform identified by number 1. Then let's run. In the folder, we see trackxz.eps. And there we see the water cylinder was rotated by 30 degrees around y-axis. That is the answer of exercise number 1. Please proceed to exercise number 2, 3, and up to exercise number 4. Then let me explain the next exercise. Exercise number 2, here we move the cylinder along the positive direction of z-axis by 50 centimeter. To do that, we use the third parameter of transform, change it from 0 to 50, and run. Then we can move the cylinder by 50 centimeter towards plus z direction. This is the answer. Then please go on to exercise number 3. All right. Now the time for answer of exercise number 3. Exercise number 3 is an exercise to rotate the cylinder around the y-axis by 45 degrees and then translate it along with the x-axis by 10 centimeter and z-axis by 45 centimeters. To do that, the first column, the first column is the first number after TR means the translation along x-axis, so it's 10, and we move the object by 45 centimeters, so the third number is 45. And the angle of rotation is no longer 30, but 45. Eventually, we can move the object in a way defined by this transform. As we do not have enough time, let me quickly explain exercise number 4. Exercise number 4 is a bit advanced one. We add another cell without defining new cell, new surfaces. To do that, we make new cell 102 filled with the water, and the specification of surfaces are exactly the same, but apply different transform number 2. And this time, transform number 2 is 0, 0, 30, and all 0 here. Oh, and I had to exclude 102 from 110. In this way, by making use of transform, we can kind of copy and paste the cells just by changing the transform specification. That's the lesson of the lecture about transform. As another 1 hour passed, let's have 10 minutes break. Please get back in 10 minutes. Thank you. So let's get back to the tutorial. As I mentioned in Zoom chat, I mistakenly forgot to take a group photo. So let's take one after this tutorial before going to next session. So we will be taking the photo in 1 hour. Anyways, let's go on to the next subject of options lecture, that is magnetic field. The meaning of magnetic field section is apparent. If you would like to apply magnetic field to bend the trajectories of charged particles, you can use magnetic field section. You can define either dipole or quadrupole magnetic field in geometrical components of Fitts geometry. If you use dipole magnet, charged particle entering from the left side of this region is bent in this way by Lorentz force. And this quadrupole or quadrupole magnetic field assumes that the magnetic field is homogeneous. If you would like to define more complicated field, you can define the map of magnetic field in XYZ or RZ coordinates by using a function named magnetic field map or magmap. You can look into this folder if you are interested in such function. In case of quadrupole magnet works as a radiation lens. If the radiation diverges in this way, this quadrupole magnetic field, which is like this magnetic field, force the particles to converge at the focal point of this magnet. Again, this is a way how we can define magnetic field. After defining a magnetic field section, please don't forget to write I mag NF equals 1 in parameter section. This is the key parameter to turn on magnetic field. Without this parameter, no matter what you do in magnetic field section, magnetic field is not activated. By defining a magnetic field in this way, you can apply magnetic fields to particles. Reg column, the values in reg column means the ID number of cells where magnetic field is defined. So these lines means the magnetic fields are applied in region 1, 2, and 3. Type parameter is either 2 or 3, meaning dipole magnet or quadrupole magnet. Gap is the half distance between the magnet poles in centimeters. This is not meaningful for dipole magnets, but this half distance is meaningful for quadrupole magnets. And in any case, this parameter is needed for the sake of the format. So you need to define certain arbitrary number, whatever, even in case of dipole magnets. Mag F is the strength of magnetic field in kilogauss. Finally, TRCL is transform ID, if you would like to define transform. We very often need TRCL transform because magnetic field section has default magnetic field direction defined in this way. So if you would like to apply magnetic fields in another direction, you need to define TRCL to rotate the magnetic fields to different axes. Initial setting of magfield.inp is like this. Please be careful that we no longer use transform.inp, but we use magfield.inp, magfield.inp input file. Magfield.inp file has 3 cells, and these two of the three cells are exposed to proton beam from the left. So please go through exercises. Exercise number 1, 2, 3, up to 4. These exercises are actually in sequence to finally strike the strike cell 101. So please do exercise number 1, 2, 3, 4 in sequence to finally strike cell 101 with a focused beam. So please try exercises 1, 2, 3, 4. And when you finish exercise number 4, please turn on yes sign. Please try. Just in case you are in serious trouble, I will be showing you the answer of exercise number 1. In the input file, please first remove the dollar comment symbol at line number 8. And please don't forget to change eye control from 8 to 0 because we want to see the particle trajectories. And magnetic field is already defined in this way. It's dipole magnet in region 103, whose intensity is 100 kilogauss. Then the beam is bent downward owing to the magnetic field in cell 103. I give you some more minutes to complete the exercises. I guess most of you are still working on it, but time is limited. Let me explain. Now it's time for answers. So, exercise number 2 is an exercise to set the quadrupole magnet in cell 103 instead of dipole. In this case, what to do is simple. At line number 50, the type parameter was 2, change it to 4. Then the particle trajectory is turned in this way. In exercise number 1, this was dipole, so the beam was bent downward, but this time it's quadrupole. It turns magnetic lens, so the beam converges at the focal point, which is at about 60 centimeters. Exercise number 3 is an exercise not very much about the magnetic field. As I said, the focal point is about 60 centimeters. This is an exercise to verify if the focal point is really at z equals about 60. To do that, we change t-track, the first t-track. In particular, the second t-track. In particular, at line number 88 and 89, NC equals 3, so that we can observe particle flux at 3 different slices. And the points to observe are 35, 45, 55. No, it's 30, 40, 50, 60 to observe the points between these pairs. So the first bin is going to be the slice from 30 to 40. And the second slice is going to be 40 to 50. And third slice is 50 to 60. And then we get track XY EPS showing the particle trajectories in different slices. And indeed, the beam focuses in a slice from 50 to 60. In this way. And final exercise, exercise number 4, is a bit challenging because we need to tune the field intensity. Correct answer is like this. By choosing the magnetic field intensity 50 to 50 and minus 150, we can precisely shoot the target, which is cell 101. As in the slide 28. So you can tune magnetic fields by adjusting the parameters in magnetic field section. And you mustn't forget to put IMagNF equals 1 in parameter section to activate magnetic field section. So let's go on to the next content, which is multiplier. Multiplier function is useful to calculate the quantities obtained by convolution. It can calculate t-track, t-cross, and t-point multiplied by energy-dependent coefficients. For example, effective dose is one of such quantities. If you want to calculate effective dose, you need to calculate convolution of particle energy spectra and effective dose conversion coefficient, which is like this one, a neutron energy spectrum convoluted with dose conversion coefficient. The convolution of this one and this one, which eventually makes scalar value of effective dose in sieverts, is obtained by this convolution. And this is a way to quick guide on how to use multipliers. Please add a multiplier subsection to the tally sections. For example, let's take an example of T-track tally. Please put multiplier subsection in this red square, which begins with a multiplier equals ALL. This means to apply multiplier to all the materials. Usually we use all, and this line is followed by MET, MSET1, MSET2, 3, 4, up to 6 at maximum. And this line is again followed by the specification of these parameters. And again, the value below MET is all usually. If you are okay with applying this multiplier to all the materials. And then you define first a multiplier set. The first value is normalization factor, which is usually 1. And this is followed by the multiplier ID. Minus 200 means to use predefined data. You can actually use your own dose conversion questions or other convolution function. And anyways, minus something means a predefined multiplier. And you can set another multiplier in this way as MSET2, multiplier set 2. And again, the values below are normalization factor and multiplier ID. In this case, minus 201. And here is the list of predefined multipliers. Minus 200 used as multiplier set 1 meant to calculate H star 10, ambient dose equivalent. And MSET2 uses multiplier minus 201. In this case, effective dose conversion coefficient based on ICRP publication 60 for AP irradiation is used. In this way, you can use various predefined multipliers useful for your application. If you cannot find multipliers that you would like to use, for example, activation cross-section or your own dose conversion coefficient, you can define your own multiplier by defining a multiplier section in this way. Let's go on to the sample input file, multiplier.inp. By running this input file with iControl 8 and 0, we get these results. The two cells in the center are iron and concrete. And this iron and concrete composite shield is irradiated by 220 MeV neutrons. Not to forget, let's change iControl to 0. So let's go on to exercise number 1. Exercise number 1 is the one to convert particle fluence to effective dose in the concrete block. By default, as we learned in basic lecture 2, T-track is a tally to score particle fluence. It's just number of particle per square centimeter per source. And here we put a multiplier subsection as well as a y-text specification in this way to get dose, which is convolution of particle fluence and dose conversion coefficients. So please try exercise number 1, and when you finish exercise number 1, please proceed to exercise number 2. exercise 1 and 2 are in sequence. And when you finish exercise number 2, please turn on yes sign. Please try. Enjoy. Now it's time for answer. Exercise number 1 is an exercise to apply multiplier. by default, T-track scores the fluence. So what we do is to scroll down to the very end of the input file so that we can apply multiplier to T-track starting from line number 106. And we type the parameters in a way written in the slideshow. And this Y text is a parameter to change the Y-axis text of EPS file, because by default it's flux, but what we get is effective dose convoluted with a effective dose conversion coefficient. Multiplier all, this is kind of a rule, and mat mset. This time we use only one multiplier, so we use up to mset 1. Mat is all, because we apply multiplier to all the materials, and a normalization factor is 1, and ID number of the conversion coefficient is -202. Then we launch FITS with this input file. In the input file, in the folder, we get trackz.eps, which is like this. The vertical axis, the text of vertical axis is effective dose picosievert per source, as we defined as Y text, and this value is a convolution of flux and dose conversion coefficient. Exercise number 2 is an exercise to change the unit, convert the unit from picosieverts to microsieverts. To change the unit, most important thing is to change the normalization factor 1e minus 6. Because picosieverts and the microsieverts are different by an order of 6. And we mustn't forget to change the unit in Y text to be microsieverts. And then we can get effective dose with the unit of microsieverts per source. This time, the vertical axis was shifted by factor of 10 to 6. All right, let's go on to the final part of options lecture. The final content is counter. Actually, this content, a counter, is very special. As far as I know, there are no default function equivalent to this one in other Monte Carlo codes. And this function is a bit difficult to understand the meaning, but if you master how this counter works, you can. And this function is very useful to get insight into the particle transport. In FITS, each particle has its own counter to identify what it has experienced, such as entering, exiting from, reacting in, and reflected in a certain region. To investigate, for example, the origin of the tallied particle, where is the tallied particle from? If we use tally in a way simple, we get all the particles entering this tally, but sometimes you may get curious to score particles which are, for example, reflected scattered in this cell, not the particle scattered from this cell. In this case, by using counter function, you can filter particles with a particular history. And again, this is a quick guide on how to use counter function. First, please define counter section, and then please set CT min and CT max parameters in tallies. And here, I in bracket in parentheses are counter IDs. And counter section can be defined in this way. It begins with a counter square bracket, meaning the beginning of counter section, and counter equals either 1, 2, or 3. And this means the counter ID number. In this case, we use counter number 1. Part equals is the specification of the particle species to which we apply this counter. And the following lines are the counter conditions. The default format of the next line is reg in out call ref. And following lines means, for example, 1 means apply this counter in region number 1, cell ID number 1, and increment the counter if a particle enters to cell number 1. This is the meaning of 1 below in. And don't do anything when particle goes out from cell number 1, and increment the counter by 10 when particle interacts, collides with the atoms or nucleus in region number 1, and do nothing for reflection. And in cell number 2, do nothing for in, call, and ref, but reset when particle gets out from cell number 2. This is the meaning of 10,000. So these numbers basically means the amount of increment. 0 means no increment, do nothing. 1 or 10 means increase the counter number by 1 or 10. And 10,000 is special because it means to reset. And actually, call among in, out, call, ref, this call can be replaced by these detailed conditions to increment counters in reactions specified by more in detail. For example, elastic scattering, inelastic scattering, fission, delta ray production, etc., etc. To try using counter function, please open counter.inp in the same folder, counter.inp. This is the input file to start with. This input file is composed of void, iron, and concrete in the same way as the previous input file. This time, the kinetic energy of neutrons is 150 MeV. Let's see, I control, let's change it to 0 and run. This time it takes a bit long, but at the end, we get the result of tallies in this way. And initially, track z.eps shows the effective dose with the unit of microsievert per source in in concrete from 30 centimeter to 40 centimeter inside this concrete, which fills cell 103. From now on, by going through exercise number 1 and 2, we are going to filter the component, three components, or to be precise, 2 components of doses attributed to neutrons scattered in iron and the ones not scattered by iron. The summation of these 2 components eventually makes the total dose, but let's, by making use of counter function, let's calculate 2 components of doses in concrete, scattered components and unscattered components. So please follow the instructions of exercise number 1 and 2 to eventually get 2 doses. In exercise number 1, let's estimate contribution of neutrons which are not scattered in iron to the dose. To do that, please copy and paste the T-track section with axis equals Z. In one of the T-tracks, add CT mean parenthesis 1 equals 0 and CT max parenthesis 1 equals 0, and change its output file name to avoid overlap. So please try exercise number 1, and when you finish, please proceed to exercise number 2 to calculate a scattered component. Please try. Time's up. Now it's time for answer. In counter.inp, as we are going to tally two more different doses, two more different dose distributions, we first copy and paste key track here. And let's rename the output file name to be T-track Z-C0 and add CT_min 1 equals 0 and CT_max 1 to be 0 to filter out neutrons which are scattered in iron. In fact, counter section from line number 58 says increment the counter of neutrons if this neutron is scattered in cell 102, which is iron. So eventually, this counter condition means to filter out neutrons which are scattered in iron. And running this input file, you get track Z-C0.eps, for example, which looks like this one. So this new result shows the contribution of the dose attributed to neutrons not scattered in iron. And this value is somewhat close to the total dose. So the indication of this comparison is that the dose in the depth of the concrete at 40 centimeter is probably dominated by this unscattered component. To make sure if it's really true, we go on to exercise number 2. And in exercise number 2, we again copy and paste T-track tally. And this time, CT_min is 1. This means to tally all the neutrons scattered once or more than once. And I've got to change the output file name to avoid overlap. By running this input file, we get new result. The contribution of the dose from neutrons scattered in iron. And this time, the dose at the depth 40 centimeter is about 10 to minus 6, which is about factor of 2 lower, not factor of 2, but about factor of 1.5 lower than the direct components. So it is true that the dose is the majority of the dose comes from the unscattered component. And this is something you can get by making use of counter function. So throughout this lecture, we learned transform, magnetic field, multiplier, and counter. That's all for this lecture. Before going to break, let's take a group photo. If you can, please turn on your camera. Thank you. Please turn on your camera to take group photo. Last time we took group movie by using Windows movie function, but this time we take still photo. Anyways, please turn on your camera. And please get ready to smile. Please get ready. Please turn on your camera. Please turn on your camera. I give you 5 seconds more. Thank you, everyone. All right, let's take a photo. Wait. 3, 2, 1, 0. Thank you. Just let me make sure if it worked fine. All right, let me take 2 more times. Again. 3, 2, 1, 0. Thank you. One more time. All right. 3, 2, 1, 0. Thank you very much. Now you can turn off your camera. Thank you very much. This group movie, a group photo is going to be shared through tutorial website. Thank you very much for your contribution. We will be having 10 minutes break before going to next tutorial on weight A. So let's have a break. Thank you very much.
Còn
Chứ đâu mình ngon thì ai xài nhiều thì nó
Okay, let's start the next lecture, advanced lecture to learn variance reduction techniques to improve the efficiency of the fit calculation from now. So I'm Yusuke Matsuya at Hokkaido University. So nice to meet you or nice to see you. The title of this advanced lecture is Advanced Reduction Techniques to Improve Efficiency of Calculation A. We called weight A. I will show you the files we're going to use in this lecture. The files are in the fifth lecture, Advanced Weight A. So please go to the folder, fifth lecture, Advanced Weight A. So repeat it again. Fifth lecture, Advanced Weight A. We're not going to use these files from now. So did you find them? Okay, let's move on to the main content. If you have any questions during this lecture, please raise a hand or send a chat message and request a breakout room. Okay, let's start this lecture. Here is the content of the lecture. First is introduction. In this lecture, first we're gonna use the INP input file in the weight A folder. Let me introduce a basic setup of the INP input file. In this input file, the neutrons with 14 megaelectron volt are incident from the air to the thick field composed of the concrete. And when executing the input file, we can calculate the neutron transport in a fixed field and we can obtain the dose rate distribution. This means stationary distribution of effective dose to depth. As in the basic setup, the number of history, please see this. The number of the history is set to be 8,000. That is, the max gas value equals to 8,000. Anyway, first let's execute the fit using the INP input file from now, and please measure the computational time, that is the calculation time of the fit code. From now, I'll make a couple of minutes, so please try this example. Please execute fits with using the input file INP input file. When you finish the fit execution, please let me know by using a Zoom reaction yes. Okay, repeat it again. From now, I make a couple of minutes, so please execute the INP input file from now. Okay, I'll execute the fit in front of you. So let's do together. So we have to, what we should do is just select the IMP input file and send to fits and execute the fits. Complete it, and after execution, you can obtain these output files, and please open the fits.out file, this one. Please open this file, and please go down and please find the calculation time at line around 416 here. In my case, the calculation time is 7.94 seconds. Looking at the chat message, the calculation time of the someone 3.19, very so quick. In my PC is slower than the user, but we can check the calculation time using the fits.out. Okay. And earlier mentioned in this lecture, we will calculate the effective dose. In general, the unit of effective dose is sievert. But as you know, the T-deposit tally enables the calculation of physical dose, such as mega electron volt or Gray. To obtain the result with sievert, you learned the previous lecture. Ogawa-san says the sievert can be calculated using a multiplier section. So we have to multiply the neutron fluence by dose conversion coefficient in fits. Let me explain the calculation method of effective dose in the fits code. In the fits code, the fluence calculated by the t-track can be multiplied with the several functions that are predefined or defined in the multiplier section. Left is depicted the how to use a multiplier section in t-track tally. And right table is the list of the dose conversion coefficient. As seen in the left, it is needed to write the MMAT and MSET1, and the MSET is composed of two parameters, C and K. C is the source intensity, and K is the ID number of the dose conversion coefficient. When writing like this, you can use the dose conversion coefficient based on ICRP 100C. That means the AP irradiation. As described here, dose with picosievert unit is calculated when fluence is normalized by the source intensity. In this time, the source intensity is not used in the scaling factor C. And the unit you finally obtain is the dose in picosievert per source. So if you like to know the detail of the multiplier section, please see the manual for the multiplier section. And when you perform the neutron dose penetration calculation using the max gas value 8,000 equal to 8,000, as shown in the upper figure, the neutron cannot go through cannot go through the depths at around 100 centimeters. Now to evaluate the neutrons going through, the deeper region, and then deeper region than 150 centimeters, we need to increase the value of max gas to 500,000. This is one of the examples. So everyone, please modify your input file, IMP input file, to increase the max gas value to 500,000. After modification, please try to execute the fit. Let's do together. We have to do is just changing the max gas value from 8,000 to 500,000, like this. And after the modification, please execute the fit. This calculation takes a relatively long computation time. So before completing the calculation, I will explain what happened in this case. As easily imagined, the calculation time is much longer, like this. So after the calculation, please check the computational time of your PC by yourself. Maybe it becomes a few hundred of seconds, like this. And from focusing on the result, this is a result after the executing of the fits with a max gas value equal to 500,000. It is, in this case, so it is needed to improve the efficiency of the fit simulation. So to improve this, to solve this problem, we will use the variance reduction techniques from now. After the execution, completing the execution of the fits, so please check the computation time by yourself. In my case, the PC is still working. So this calculation is a very long time. So let me explain the concept of the weight in Monte Carlo simulation calculation. Here is the concept of weight in Monte Carlo calculation. I will briefly explain the concept in the case of track length study. The weight of track length study can be calculated based on this equation, where the L is the track length of the particle, and the W is weight of particle, and N0 is the total history number. In normal calculation, the default setup and the fits code, the weight importance of the particle in Monte Carlo simulation is always unity. When using the weight larger than 1, the manipulating the weight to artificially cause the events that are statistically unlikely to occur. However, please note that if you manipulate the weight, you cannot calculate the frequency distribution for each history. Okay, let's move on to the second step. Oh, my PC is very slow, so the previous calculation has not been completed. Maybe I hope that your calculation completed. Okay, let's move on to the second. Second is neutron deep penetration calculation using the importance section, particularly geometry splitting. I'll explain the geometry splitting and Russian roulette. This is so-called the cell importance method. Okay, here is a brief explanation of the cell importance method. In this method, first, users have to set the important I to each cell. When a particle passes through the border of cell ID number 1 and cell ID number 2, then second, this method automatically calculates the ratio of I value. So I2 value divided into the I1. Then when the ratio of I values are larger than unity, looking at here, for example, when a ratio of the value is larger than unity, an incident particle is split into two, into the ratio. For example, when the value is an integer, but when the value is an integer, in this case 3, a particle is always split into the integer value, in this case 3. When the value is not an integer, a particle is split into 3 by 75% and split into 2 by 25%. Meanwhile, when the ratio of I value is smaller than unity, the particle generation follows the Russian roulette, which is the killed or alive. This means in the case of the right figure, the particle is killed by about 33% and alive by about 66%. Anyway, let's learn the importance section by actually using it. Everyone, please execute the imp-hist.inp file and check the neutron trajectory. So let's try it. From now, I'll take a couple of minutes. So please execute the imp-hist.inp. If you finish this example, please let me know using the Zoom reaction. Yes. Repeat it again. Please do this example. So please execute the imp-hist.inp and check the neutron trajectory. The input file, imp-hist.inp, is different from that we used previously. So please be careful. imp-hist.inp file is this one. So please execute this input file. Okay, it's time. So let's try it with me. So I'll do this example, just executing the feeds. Maybe calculation is so fast like this. Okay, finished. After the execution, you can obtain this result. This result, imp-trajectory.eps. Please open this file. And as shown in the right figure, the neutron goes through from the region 10 to 1 and from 1 to 2, like this. So after the execution, repeat it again, please open the imp-trajectory.eps file, this one. In the basic setup of imp-hist.inp, the 5 megaelectron volt neutrons are incident from the left side to and go through in the concrete, and in this basic setup, the importance value for all regions are unity. The importance value for all regions are unity. So one particle goes through in the regions 10, 1, and 2. Then let's increase the value of importance like this. So please modify the value of importance in the region number 1 and number 2 to 2 and 4 respectively. In the same manner as the previous example, please modify the input file and please execute the fits. I'll make a couple of minutes in the same manner as the previous example. So please try this example. Sorry, I forgot to say. So when you finish this example, please let me know using turning on the Zoom response. Yes. Everyone, thank you very much. Okay, I'll demonstrate it. So what we have to do is just modifying the importance value at line 62, 63, like this. The number of importance value of region 1, like this, and please change this value to 4. After the modification, please execute the fix. Okay. After the execution, please open the, what is the name? I forgot. Please open the imp-trajectory.eps file. As shown in this figure, graphs of the imp-trajectory EPS changed like this. In this case, the value of importance in region number one and number 2 are 2 and 4 respectively. A neutron, as shown in this figure, a neutron goes straight in the region number 10 and split into 2 here in the border between the region number 10 and number 1, and split into 2, and one still goes straight in the region number 1, and the other react with the react with sorry the other particle react with the region number 1 and change the angle like this and go through in this direction. So the number of particles increase. So next, let's decrease the value of importance like this. In the same manner as the previous example, please modify these values of the importance in the region number 1 and region number 2. Please modify the value of importance in region number 1 and region number 2 to a half and a 1/4. After the modification, please execute the fix, and after that, please open the EPS file imp-trajectory.eps and please check the results. I'll make a couple of minutes, so please try this example. Okay, let's do this with me. So please modify these values like this. The value for the region number 1 to a half, and this one, please change the 4 to 1/4 like this. And after that, please execute this input file. After that, please open imp-trajectory.eps. After the execution, the graph of imp-trajectory.eps changed like this. In this setup, the value of importance in the region number 1 is a half. For this region, in this case, the neutron is killed in here. So the surface border of the between the region number 10 and region number 1. Then let's increase the importance extremely. Please modify the value of importance in region number 1 and region number 2 to 2 and 100 respectively. In the same manner as the previous example, please modify the input file and then execute the fix code. Repeat it again. please modify your input file so as to write down the importance value to be 2 and 100 like this. Okay, let's do this with me. So where is my folder? I found it. So in this example, please change this value like this. Then after that, please execute the bits. After the execution, please open the imp-trajectory.eps file. As shown in the right figure, the graphs, the fluence, the result of the neutron fluence shown in the imp-trajectory.eps changes like this. In this setup, the value of importance in the region number 1 and region number 2 are 2 and 100 respectively. So for this region, the neutron split into 2 in the region 1 and 1 neutron split into 50 in the region ID number 2. So meaning the 100 for 2 neutrons in the region 2 in total. I hope that you have understood how to use the important section from my explanation so far. So then let's do one more example for important section. In this example, we will use the imp.input file we use at the beginning in this lecture. Everyone, please activate the importance in the imp input file. And after the activation of the importance section, please execute the bits. I will show what we should do. So please open the imp.input file we use at the beginning of this lecture, and please go to the importance section here. In this situation, this section is inactivated, off is described. So please delete the off and activate the importance section like this. And after this condition, making this condition, please execute the bits. And please see what happened in this case. Okay, I will execute the bits. So please follow me. Maybe this calculation also takes a relatively long period. Right. So let me explain the importance section used in this example. The importance section activated in this slide is shown in the light blue box. As shown, the ratio of importance value between the adjacent regions is set to be 2.5, 2.5, 2.5, 2.5, like this. So after the completing execution of the fits, please open the imp-dos-xz.eps file. Then you can obtain these kind of the figures. You can obtain these figures. The upper figures shows the results we simulated at the beginning of this lecture. So comparing this result and this result, so as shown in the current calculation result, the more neutrons successfully penetrate to deeper location with reduced calculation time, maybe. Maybe this calculation takes a relatively long time. So please continue the calculation. So, and let me explain this lecture. Here is a comparison between the depth dependency of effective dose with importance using the importance section and that without the importance section. It should be noted that the lesion number, the horizontal axis, is roughly proportional to the depth in centimeter, roughly proportional to the depth. From the figure, the importance section, importance enabled the neutron deep penetration calculation with high efficiency with a reduced statistical error. Still working. Okay, let me explain the importance notion. So I will explain the important notion of setting of importance section. That is, it is better to set 2 to 3. It is better to 2 to 3 for maximum importance ratio between the neighboring cells, meaning the upper setting is good, but lower one is a bad example. When trying the bad example, you can have these outputs. When trying a bad example, you can have these output files. The right shows a bad setting of importance section. The importance ratio between the cell ID number 5 and 6 is very large, so larger than 3. In this case, as shown in the lower figure, the relative errors become too large in comparing with the previous setting. My PC is still working. Okay, let me explain the lecture again. Okay, let's move on to the third because now we have 10 minutes or 20 minutes for this lecture. So let me explain the forced collision finally. Okay, let's move on to the third. We are gonna calculate the particle production in thin target and run the forced collision. Initially, I will explain what the forced collision is. To put it in one word, the forced collision is a fixed function that the radiation can be forced to collide with a very thin target. Using this graph, I will explain. The left is a normal calculation without the forced collision section. In general, the frequency of the collision of 100 megaelectron-volt proton with a 10 micrometer thick silicon, which is located here, is extremely low. So as shown, no collision occurred in such thin target. It is natural, but if you want to evaluate the secondary particle generation from the collision, it is needed to transport a large amount of protons. So it takes too long calculation time. To solve this problem, the forced collision section is useful. Right is a calculation using the forced collision section. As seen in the right illustration, sufficient amount of secondary particles, the colored area, are generated from the target. Target is located here. Repeat it again. Target is located here, and the proton beam are incident from left side to right side and collided with the silicon target here. Therefore, as for the application example, we can evaluate the particle production measurement with a film. Then, in this lecture, let's perform the simulation of particle production measurement with a film. From now, I will use the forced.inp file. I will explain the basic setup, the forced.inp file. In this input file, two types of tallies are defined. One is the T-product tally that can sample the energy distribution of alpha and silicon ions produced in a target, which correspond to true cross-section. The other is the T-cross tally that can sample the distribution of alpha and silicon ion in a detector, meaning the measured cross-section. In addition, the proton with 100 megaelectron volt are incident to the thick silicon target like this, and the detector is located in this position. Okay, from now I will make a couple of minutes. So please execute the force.inp file. Repeat it again. So everyone, please execute the feeds using the force.inp file. When you finish the feeds execution, please let me know using the reaction button yes. Everyone, excellent. Okay, I will do this example from now. So let's do it together. So where is the force.inp? I found it, this one. So please, just executing feeds. So please execute feeds like this. Oh, completed. Okay, after the execution, please open the product.eps file and the cross.eps file, this one, and this one. Then, as you can see, this result, you can confirm that without the forced collision, protons do not collide with the film. So there is no result about the cross-section. This is a problem, serious problem. So to solve this situation, the forced collision is useful for analyzing the secondary particle generation from the film target. So please see a central figure. Sorry, due to the time constraint, so I will omit the details, but in the forced collision in the pits, the particle is split into two particles like this. One is the uncollided particle, and the other is a collided particle like this. In other words, the particles are forcibly generated. The method of the forced collision decreases the history variance, but calculation time per history increases. In this section, you have to define the FCL value, which means the forced collision factor. The negative value applies only to particle entering the cell, and the positive value applies all particles surviving weight cutoff. Anyway, let's force particle to collide with the film using the force.inp. In your input file, you can see the forced collision is inactivate. So please open the force.inp and looking at the lines around 73 to 76. So the forced collision inactivate. So please delete the off and activate the forced collision section like this. From now, I'll make a couple of minutes. So please execute the fits with this input file after this modification. Repeat it again. Please try this example exercise. So after the modification, deleting the off, and please execute the fits, and please see what happened in this case. After you finish this fits execution, please let me know using the reaction button yes, if possible. Thank you very much. Okay, let's do this example together. What we have to do is just deleting the off. After that, please execute the fits. Please execute the force.inp file. Okay, finished. After the execution, please, in the same manner as previous example exercise, please open the product.eps and cross.eps file. I'll explain using this presentation slide. As shown in the right upper figure, I can confirm the generation of alpha particles and silicon ion in a film. However, checking the cross.eps file, in this condition, the weight of particle produced by forced collision are below the weight cutoff WC2 value that is defined in the parameter section. So it is hard to transport secondary particle due to the Russian roulette. So to transport secondary particles produced by forced collision, you need to modify WC2 value. So next, let's set a small number on weight cutoff WC2 in this example. So from now, I will make a couple of minutes. So please modify the parameters section like this. And after the modification, please execute the feeds with this input file, force.inp. Repeat it again. Please execute the feeds after modification like this. Then please execute the force.inp. When you finish this example, please let me know using reaction button. Yes. Okay, let's do this example so together with me. So what we have to do is just defining this WC2 value like this. So please delete that dollar mark like this, dollars mark like this. And after this modification, delete the dollar symbol and please execute the feed. Okay, completed. Then after the execution, please open the track-xz track-xz.eps file. Track_xz.eps file. And please open the cross.eps file. Let me explain what happened using this slide. So you can obtain these kind of the results. So you can confirm the secondary particle transport like this. From these, we can discuss that the experiments cannot measure the silicon production cross-section. So focusing on this. Repeat it again. We can discuss that this experiment cannot measure silicon production cross-section correctly because many silicon are stopped within a target. Okay, let's see summary. Really sorry for my quick explanation of this lecture. So let me summarize. So summarize this lecture. In summary, we learned the variance reaction techniques such as importance and forced collision section. First, cell importance method is effective in deep penetration calculation. Second, the ratio of importance between neighboring cells are better than less than 3. So the appropriate the setting of importance is very important. And there is another technique, weight window generator for complicated geometry, which can be run in weight B, maybe tomorrow's lecture. Third, the forced collision method is effective to calculate the particle production in a thick target. That is all. Thank you very much for your kind attention. Ogawa-san, now that we have finished, please make an announcement for tomorrow.
Thank you, Yusuke. I'm taking over the screen to close this session today. So now we are at the end of the lectures today. We will be resuming from weight B, which Yusuke mentioned just before. So, as usual, we tutors take your questions from some 10 minutes from now on. If you would like to discuss with us, please raise hand. You can discuss with us in person in breakout sessions. As usual, Zoom session opens at 10:30 UTC and tutorial begins at 11 UTC. Please answer survey by Friday from URL here or QR code here. Tutorial videos and charts are available from URL here. The video recording of all the lectures today is going to be available in 2 or 3 hours. Please install Python and its libraries to take the optional course, Medical Data Treatment by RTFITS on Friday. So this concerns those who are using either Mac or Linux and going to take the optional course of this one. So Windows users or those who are not, who are going to take other lectures, please forget about this. And if you need a certificate of participation, please send an email with the title certificate request to an address fits.en-tutorial@jaya.go.jp with text body, your title, plus your full name. Just sending once is fine. We can issue a certificate of participation for 1 week. If any questions, please raise your hand and wait for tutors. If no questions, please leave the session. See you tomorrow. Thank you very much. See you tomorrow. Have a nice day. Have a nice evening. Thank you very much. Bye-bye. Thank you very much. See you tomorrow. I hope you enjoyed the tutorial today. Thank you very much. See you tomorrow. Thank you very much, everyone. Bye-bye.